Well, good morning, everybody, and good afternoon or good evening to you all, depending on where you're uh, viewing the presentation from. My name is Gene Bohensky. I'm the Director of Application and Partner Learning at Perma. This presentation is going to cover some experiments that we did at Perma a couple of years ago to really understand the effects of sample conditioning on the SO2 retention and measured emissions. This is the first time we've really done this type of work in-house, and we came up with some really interesting results. So I'd like to share those with you today. As you know, in the SEMS world, that's continuous emissions monitoring world, our products are present helping companies be able to measure SO2 at very low levels. It's one of the hallmarks of our products that we're able to retain the SO2 because it's otherwise water soluble. When you use a cooler, the coolers condense the water out and you lose some of the SO2. This is something we did to really prove this effect and understand the differences between coolers and our Nafion dryers, and as well as other methods, which we're going to be covering today. So as an introduction, this testing was done at Perma by Amy Geary and Craig Sunada. Craig Sunada was formerly our VP of New Product Development, and Amy Geary was a technician with us. They performed this work in-house. Just to begin, there's a couple of different gas emissions analysis methods. There's in situ, where you actually have the analyzer and the sample extraction directly on the stack, and you're measuring the sample right there on a hot and wet basis. There's also extractive methods where you're pulling out the sample and then you're bringing it to the analyzer in a shed someplace. Those can either be done hot and wet. That means you're taking the sample and you're putting it through a heated line, and you're measuring it a hot and wet method. There's also a dilution, where you can dilute and analyze that. And then the cold and dry extractive method, which is what we normally pay attention to ourselves, because most analyzers want the samples cold, clean, and dry, and they come off the stack hot, wet, and dirty. So one of the challenges some of the other methods have is that they run into problems with long-term reliability because of the difficulty in the actual sample itself. It's corrosive, it's dirty, it's hot, and it's challenging to get accurate measurements over time. So in this presentation, we're going to cover the background first, problems with SO2 analysis. We're going to show our laboratory testing and field data of Nafion versus a condensing cooler. And then we're also going to show some laboratory data using an FTIR analyzer with dry versus humid samples, because we found some interesting things there. And then we're going to summarize our results. So let's start with talking about cold and dry extractive conditioning methods. Really what we're doing is we extract the water from the gas streams or eliminate it. You need to do this because otherwise, basically, your water has two main issues with a sample stream. First of all, and most importantly of all, the water, if you get liquid water in the analyzers or on the analyzer sensor, the analyzer will not work. You'll ruin your analyzer, which is a big repair. So we need to extract the water from that. And the other thing we need to do is get rid of the water that doesn't interfere with the measurement. So the most common way that the water is removed from sample streams is with a condensing cooler. That cools the humid gas to 4 degrees C and decreases the dew point of the sample gas also to 4 degrees C. This works well with insoluble analytes. So if you're measuring CO2 or measuring other type of analytes that are not soluble in water, this is not an issue because it takes the water out reliably and effectively. But soluble analytes are sometimes lost, and here specifically we're looking at SO2, where at 70 milliliters of SO2 per 100 milliliters of water dissolves at 4 degrees C, and you can see SO2 solubility in water increases as the temperature decreases. So when you're chilling it, you make it possible for the SO2 to be soluble in water. There's other things that are soluble in water. The NOx as well is soluble in water, and as a result, that is also lost, but we're not really talking about that in this, this comparison. Right now, we're just focused on SO2. One of the reasons SO2 is such a concentration point is because in many areas of the world where the pollution is really an issue with horrible air quality, the requirements from the governments to eliminate SO2 are becoming stricter, and as a result, the levels of SO2 that need to be measured coming off the stack are actually much lower. So in the past, you might be able to live with 100 or 200 or 250 ppm SO2 in your exhaust gas. That's now no longer allowable. There's many places that are mandating 20 or 50 or 5 or even less ppm SO2. And in those cases, a standard cooler is going to have trouble because it's going to lose part of what you're measuring. And that's what we're trying to demonstrate here in this presentation. So with Nafion-based cold extractive conditioning, the Nafion is a water selective permeation membrane. That means water is transferred from one membrane side to the other on the basis of differential vapor pressure. And it's done in the vapor phase. So we can remove the water without condensing the sample. The Nafion material, because it's based on Teflon, is highly resistant to corrosion, and it allows for low-level humid SO2 analysis. That's really its claim to fame in the SEMS world. We have over 40 years experience drying samples in this way. So let's look at what we've done in our laboratory. In our laboratory, we used a Nicolette IS50 thermoscientific FTIR. We used an 80 degrees C gas temperature with a 43 degrees C dew point, or 8.5% water vapor. And we're looking at an SO2 concentration of 15 to 19 ppm. So we used our Gas 6080 Nafion system that's shown on the top right there. That's one of our systems we build. And below is our test setup where we are generating the sample gas and putting that into the sample conditioning system to remove the water, and then we're analyzing that with the FTIR. This is we try to emulate a typical sample gas that we see at some of our customers. Really, we have a lot of experience with this type of application. The first place in the world that required this type of low-level analysis was in the Southern California emissions district there, but in the LA basin, where they've discovered early on that the coolers lose just about all of the SO2 that is present in the sample gas. And so when they started installing our Gas 2040 systems, they found that we were able to retain the SO2, and as a result, our products have become very popular in that region. That's really where we've developed a lot of our long-term history. Of course, we've transferred a lot of that history and experience into the Chinese market, where they have similar requirements to measure low-level SO2. Of course, we have a big customer that we supply dryers to for their own sample conditioning system for the marine SEMS market, where they're also required to measure low-level SO2 coming off the stack. So all of this is kind of pointing to us as the manufacturer of Nafion dryers, because we make it possible for them to accurately measure these sample streams. So let's take a look here at a hot-wet analysis and a comparison of IR spectra for water and SO2. You can see water on the top and SO2 on the bottom there, and you can see that there's some little peaks of water that could possibly interfere with or affect the SO2 measurements, and we'll come to that a little bit later. But that's something you can see on the graph here. Let's show here how we humidified our calibration gas. So we got the calibration gas with a certain level of SO2, and we needed to humidify it properly in order to make the measurements. And of course, we had to humidify the gas with one of our humidifiers using the same PD dryer. In order for us to do this, it had to be humidified in the vapor phase so we don't have any condensing water and lose the SO2. So what we did here is we took our instrument air, and first what we did, this is very important, what we did was we humidified the instrument air with a humidifier using water to gas humidification. That allows us to get a very efficient and a very high level of water vapor into this gas. And then we mixed it with the calibration gas, and we mixed it in the vapor phase, and you can see that down here. That we did on purpose because we were able to control precisely how much water we wanted in the gas. We also did not want to humidify the gas directly with water because we found that you will get some losses that way. So we first humidified the air that was going to be used to mix with the calibration gas to get us our test gas. So let's look at our Nafion apparatus here. You can see we have on the top, this is the humidification of the calibration gas. That goes into our sample in here. That goes into our dryer, and then from our dryer we have our Defender humidity sensor to detect the humidity coming out of the Nafion dryer, and then from there we go into our FTIR spectrometer. So we're able to tell, do a before and after. Right? We can with these valves here we can control directly what's going into the FTIR. We can use the gas that's coming right off of the calibration section. So we know that that's test gas A, and test gas B is the gas that has gone through the Nafion dryer. Similarly with the cooler, we use our same calibration gas humidification setup here, and then instead of our sample gas, we're using the cooler and doing the same thing where we can test A/B test before and after. Okay. So let's just take a look at the drying performance of the sample conditioning system. So we're not looking at losses yet, we're just looking at the drying performance of the Nafion dryer in this experiment versus the condensing cooler. And the red line here shows our temperature and our dew point temperature of our exit gas. And you can see the cooler, when you switch that on, it takes a couple of seconds to get right down to its +4 degrees C. That kind of stays there on a constant level. With our Nafion dryer, you turn it on and it drops right to about 10 degrees C, and it takes a couple of seconds more before it gets to your stable dew point, in this case roughly to -10 degrees C dew point. So we have a dew point difference here between +4 and -10 of drying the sample, which, as we said, was 80 degrees C, 43 degrees C dew point, which equates to roughly 9% water by volume. Now let's look at our results of the condensing cooler system. This is our A-B results. So you could see the basic So2 concentration that was generated by the calibration, the humidified calibration gas was roughly 15.3 parts per million. When we turn on the cooler, our average out was 7.9% for a 48% loss. When we turned off the cooler, we went up to 16.8 parts per million. We turned on the cooler again. We got to 32% loss, roughly 11.5 parts per million. Okay, so that's the difference between your inlet and your outlet of the cooler. So let's take a look at our Nafion conditioning results with So2 retention. Our inlet here was 17.2 parts per million. And when we went through the dryer, our average was 17.42. And then when we turned back to the original gas, we were up at 17.67 parts per million. So you can see there's really no significant losses from using the Nafion dryer to dry that sample gas. That's a significant difference. No losses versus 30 to 40% loss. So let's look at some field data using some NDI analyzers at a power plant in Zhengzhou in China. This sample was at 55 degrees C with a 15% moisture content. We had an So2 concentration there of 23 to 27 parts per million, and an NOx concentration of 65 to 73 parts per million. And in this case, we're going to compare the condensing cooler with our Gas 35 Nafion system. Our Gas 35 is a portable system that we can use and bring into the field and get those differences right away. So let's look at our NDIR analyzer results. Test 1 and test 2 are using the standard, that's the fixed system in place there, using a condensing cooler. NDIR analyzer 1 shows an So2 parts per million of 0 and an NOx of 86.93. And condensing and test number 2 with analyzer number 2 shows a So2 parts per million of 0.76 and NOx at 43.44. One of the challenges of showing a measurement of 0, which is actually common in a lot of installations where you have low-level measurements, the problem with 0 is that you don't know whether that's the actual reading or the equipment isn't working. Of course, whenever there's a 0, the biggest issue is that most people don't accept the 0 because there's no confirmation that the equipment is actually working. And that's one of the things we always want to avoid in the field. You got to have some results. You got to have the equipment show that it's working and it's calibrated properly. Let's look at those same conditions again with the Gas 35, with test 3, with NDIR analyzer number 1. That's the same sample as in test number 1. There we have an So2 parts per million of 27.51 and NOx is 84.76. Test 4 shows also a similar So2 level of 27 versus the NOx at 43.44. So what's interesting here is you could see that in this particular case, all 27 parts per million, just about all that So2 was lost with this particular condensing cooler. But what was very interesting about these results is test number 5. When we used an FTIR analyzer with no conditioning system, that means we're actually looking at the hot-wet sample direct off the stack, we found some losses. We saw 22.92 parts per million So2 and 78.24 parts per million on the NOx. So that was a little bit intriguing to us. And I think what we wanted to do later on is try to prove that in the lab And we actually found that using with our laboratory data, we wanted to go back afterwards and see if we can confirm that. So we did an experiment with SO2 concentration at 6 to 15 parts per million and CO concentration of 9 to 23 parts per million, water content of 0 to 14%, and with a commercial FDR analyzer. We had 3 tests: one dry gas standard test, dry standard gas sent to the FTIR. Then we test number 2, humidified gas sent to FTIR. And then test 3, humidified gas dried with gas 35, a Nafion system, and then sent to the FTIR. So let's look at these setups. So here, test 1, what we were doing is just taking the instrument air and mixing it with the calibration gas to send to the FTIR analyzer. The second one is using a humidified instrument air and mixing it with the calibration gas to the FTIR analyzer. And then the third test was similar to what we showed you on how we did the tests on the Nafion system, except this time we used the gas 35, not that gas 6080. So we took that humidified gas and we brought that into the gas 35 system. And then after that, after it was dried, so we humidified it, then we dried it, then we brought it to the FTI analyzer. And these were our results, which are very interesting. So with our dry standard gas, with our low concentration SO2, we were at 6.49, high concentration SO2, 15.04, and low concentration CO2, 9.78, and high concentration, 22.89. What was interesting on test number 2, with high temperature and high humidity, is that our low concentration SO2 was measured at 3.82, and the high concentration at 12.38. So it looked like here that we're losing roughly 2.6 ppm SO2 in these measurements. And of course, when we did test number 3, when we humidified it and then dehumidified it again, we are at 6.23 and 14.66, which was almost the same level as test number 1. So what this showed us is that with an FTIR, drying the sample actually gets you a more accurate result, that there is some sort of issue with water present that throws off the FTIR measurements somewhat. And we believe that this has to do with with what we showed before, where you have your water spectrum and where your main SO2 peak, that there could be some sort of interference there, or some sort of adjustment in the measurements based upon water being present. In any case, we see that as leading to some inaccuracy that really no one has been able to explain why that occurs. So let's go through a final summary. With cold and dry extraction, condensing coolers lose the target analyte, and that's really why our products have become so important in this industry, because when you're looking at low-level SO2, it's really the Nafion dryer that's going to preserve that SO2 in the sample and get an accurate result. And I think that that's very important to note. And a lot of people are using the alternative hot-wet extraction, but we're seeing a water interference there that is changing the measurements. You're also not getting the best results with FTIR, and you might be underreporting the level of SO2 in those measurements. And also calibration is difficult to get that to work properly. So in summary, it really points to the Nafion dryer being the ideal way to dry your sample gas to preserve your SO2 measurements. So that's really what the end result is. Nafion systems do not cause SO2 losses, selectively removes water, and lessens water interference in hot-wet measurements.